Recording in progress.
All right, folks, welcome back to our conversation about chemical equilibrium. In our last video, we had a general overview into what equilibrium is, how that applies to a chemical reaction, and some common misconceptions that people tend to hold on to when they think about chemical equilibrium. So let's make sure we avoid those misconceptions and stick with our definition of equilibrium, because now what we're going to do is we're going to look at chemical systems that exist in a state of equilibrium and ask ourselves what might happen if that state of equilibrium is disrupted. So let's talk about disturbances or disruptions to a state of equilibrium. We have this beautiful little guide called Le Chatelier's principle, which makes a statement about systems at equilibrium essentially wanting to maintain equilibrium. So they will do whatever they have to do in order to get back to being in a state of equilibrium. So let's write this. Le Chatelier's principle states that a system or a reaction here will adjust to reestablish equilibrium when the reaction equilibrium conditions are altered. So let's think about what that looks like, meaning what on earth is happening when we're talking about equilibrium conditions being altered. So remember, at equilibrium, the concentration of reactant and concentration of product is overall a net constant. So again, like they're constantly changing, but the change is not something that we notice as being like observable, because for every like decrease in the concentration of reactant, that then gets reversed in the state of equilibrium, right? So at equilibrium, it's kind of okay to say that our reactant and product concentrations are constant. So a disruption I could make to this state of equilibrium is a change in the amount of reactant or product. So that is one way that I can throw a system that was once in equilibrium out of equilibrium. How about another way that we could potentially, alter, adjust, perturb, disturb a system at equilibrium? So at equilibrium, our reaction exists in a kind of thermodynamic equilibrium as well. Meaning the energetics involved in that chemical reaction is something that is like being, changed in the forward and then unchanged, like reverse changed, undone in the reverse. So you've got this thermodynamic equilibrium. It's not the same thing as thermal equilibrium, right? But we have a thermodynamic equilibrium. So how could we then adjust some condition of our system to affect that thermodynamic equilibrium? We could possibly change the temperature of the system. And another means that we have of changing a stated equilibrium is at equilibrium if our concentrations are more or less constant, then if we're looking at a gas phase reaction, we could alter this equilibrium by changing our pressure. Right, so all of these external factors that have some kind of effect on how a chemical reaction proceeds will also disturb or change the equilibrium of that chemical reaction. So let's look over here at an example. So we are looking at the reaction between nitrogen gas and hydrogen gas to form ammonia gas. This is an exothermic reaction, and I've indicated that by showing that delta, which is our stand-in for heat, is shown on the product side. Heat is produced, right? Exothermic. And let's look at the case of when we exist in equilibrium. So here we are existing in equilibrium. And this would be our system kind of like before we disrupt it. So now we've got this interesting time point here during the reaction where hydrogen has been added. So we have increased the amount of hydrogen reactant that is in the system. So in order to reestablish equilibrium, or the state at which the production of ammonia and reproduction of nitrogen and hydrogen have equivalent rates, then we're going to see a spike, like a really rapid increase in the rate of the forward reaction, because we want to really get rid of that excess hydrogen that we added. So I'm going to draw this like big arrow here. So this increase is a huge favor toward the production of products. So we call this a shift or a favoring toward product. Because the reaction rate of the forward reaction has spiked. Once that reaction rate has like increased, right, we rapidly start consuming hydrogen. Then we see our system begin to go back to consuming our reactants at a rate, producing our products at some rate until a new equilibrium is established. And notice this equilibrium is at a completely different reaction rate. So if this was like the initial equilibrium state, then here we have this new state of equilibrium reached where forward and reverse are happening at the same rate. But the rate at which those forward and reverse parts of our chemical reaction happen are now a little bit faster compared to before, because we've got more stuff. We can also look at the reverse of this. So like, what if we were to take hydrogen and remove it from the system? So like, let's call this example A, where we're looking at increasing the amount of hydrogen. And then we'll look down here at example B, where we are decreasing the amount of hydrogen. So if we decrease the amount of hydrogen, then our reaction has been shifted out of equilibrium and needs to reform that hydrogen in order to achieve a state of equilibrium again. So how does that happen? If we've got a lack of reactant, then the reverse reaction rate, that's what's going to spike. Another way to think about it is the rate of the forward reaction is going to drop. So we've got here a state of equilibrium. So this is our initial equilibrium state. And then the forward reaction is going to drop significantly or be much slower than the rate of the reverse reaction. So if this was looking at what happens when you increase the amount of hydrogen, then if I were to compare my forward reaction compared to my reverse reaction rate, when we remove hydrogen, we would see that the reverse reaction rate would be much, much larger, right, compared to the forward. So we see here a drop in the reaction rate of the forward reaction. And that is our adjustment to the fact that hydrogen has been removed, right? We need to rapidly consume ammonia to remake that hydrogen. So the reverse reaction rate would spike and the reaction rate of the forward would drop. And then once we have kind of like our initial starting reaction rates, we can go to our classic reaction rate will equilibrate until we reach a new state of equilibrium, which is where we are here. So this is our new equilibrium. Whoa. New equilibrium reached. Forward, reverse are the same rate. Notice this is a little bit lower because we did see a drop in the rate of one. Whereas this one was a higher rate. So on the next slide, what we're going to do is we are going to practice predicting how reactions like this one might be affected by changes in quantities of substances at equilibrium, changes in temperature of the system at equilibrium, or if we're looking at gas phase reactions, the change in a pressure of the system. So let's look at a couple of general reactions. Let's predict how the reaction will adjust to reestablish the state of equilibrium upon some kind of change. So for our first reaction, we've got, let's do A going to B. And let's see here, this is now at equilibrium. And if I'm going to increase the amount of B, what's going to happen? So according to Le Chatelier's principle, if I have now disturbed my system so that I have more B than there was at equilibrium, then I'm going to see the production of B rate drop, or inversely, the rate of unforming B increase, so that we can re-achieve a state of equilibrium where we have constant concentrations of A and B. So if we increase B, then we expect to see a shift left or towards A. So if we're thinking about what's going on with B, this would momentarily favor the left, so the rate of the reverse reaction would spike. All right, what if we had something like, C goes to 2D, and these are gases. And let's say we increase the total pressure of the system. Now, this one is interesting in the sense that it has to, like, it forces us to remember our kinetic molecular theory of gases and all our conversations about like gas behavior from Gen Chem 1. So notice in this reaction, my reactant C, I've got 1 mole of it in proportion with 2 moles of product D. So if I increase the pressure of the system, I would see more collisions on the side that has D, or that part of the reaction where we have D present, which means that more collisions means more encounters of our molecules, right? We're thinking about reactions like this. They encounter one another and then form product. So if I've got a higher pressure, then I am going to shift left, or to be more specific, shift towards the side where the moles of gas is less. And this is because I've got more collisions on the side of the reaction with more moles of gas. So this would also be a shift, in this case, left. So I would see a momentary spike in the rate of the reformation of C until we gradually reestablish equilibrium. Okay, let's look at this reaction. So I've shown X going to Y. So that is our chemical system that is in equilibrium. And I have indicated that heat is being consumed, right? So heat is required for this reaction to proceed in the forward direction. So I'm treating heat like a reactant. And what's going to happen if I increase the temperature of the system? So if I increase the temperature of the system, and heat is something that is driving the forward reaction, then I'm going to see a momentary shift or increase in the rate of my forward reaction to consume that heat to regain our thermodynamic equilibrium that we've established initially. So this would be what we call a shift right, or a shift towards product, here Y. And then let's look at just something a little more complex. 2p plus q exists in equilibrium with R and 3s. So what happens if we remove R from the system? So we are decreasing the amount of R that's present. So if we were to remove R from the system, then we would need to find a way, us being the system at equilibrium, to reestablish the amount of R that we've got to be back at some constant quantity. And the only way we can do that is by momentarily favoring the production of R. So the rate of the aspect of the reaction that forms R would increase. And this would be another rightward shift. Or shift toward product. Here, shift toward R. So these are the adjustments that are made by Le Chatelier's principle. Like what I've drawn here, and how our system will momentarily correct or make a change into the rate of the forward or reverse reaction. So this is the adjustment, 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 adjustment here. And these are all adjustments that we are predicting using Le Chatelier's principle. So again, we see like a momentary favoring or shifting or increase in the rate of one half of this coin. That is our chemical reaction, until we reestablish a new equilibrium where the rates of the forward and reverse are equivalent. All right. So far, our conversation about equilibrium has been innately qualitative, right? Like we've been describing a lot of like conceptual ideas of what's going on at equilibrium. However, the nice part about chemical reactions and like what chemists tend to have fun with is that we can calculate actual chemical quantities by using stoichiometry. So how do we then quantify, meaning use numbers, to just like, how do we quantify or describe a system at equilibrium? How do we use numbers to describe a system at equilibrium? Like, what is the means that we have available to us to like numerically expressing something that's happening at equilibrium? And what we have is this notion of the equilibrium constant K, sometimes written like generally KEQ. So let's define the equilibrium constant KEQ, or an equilibrium constant All right. So an equilibrium constant is a value that demonstrates a relative proportion of reactant and product concentrations at equilibrium. So what would that look like? So relative proportion of reactant and product concentrations. So here's what I'm going to do. I'm going to look at this reaction as an example, and then I will give you like a very general definition of an equilibrium constant. So if we're talking about an equilibrium constant, we have to be in a state of equilibrium. So let's look at this diagram and identify which of our four boxes shows us existing in a state of equilibrium. So where the reverse and forward rate of reaction are equivalent. So here in this first box, we've got all reactants. So this is our initial condition. This is where the rate of the forward is going to be much, much larger than the rate of reverse. We're going to start consuming reactants pretty rapidly. The next box, this one here, is looking a little bit further down the line in the chemical reaction. We've begun to form some product, N2O4. However, we are still in the process where we have a larger forward rate than we do reverse rate. So we have not yet achieved any state of equilibrium. So this is some like at T reaction. So at some time during the reaction that is pre-equilibrium. And then looking at this third box, this is where we see our rates of reaction in the production of N2O4 and the production of NO2 being equivalent to one another. So this is where we are at equilibrium. So I'm going to focus on this box because when we're talking about equilibrium constants, we're talking about our state at equilibrium. So if I wanted to write the KEQ for this reaction, or the equilibrium constant, what I would be looking at is, let's look at our definition, a relative proportion of reactant and product concentrations. So relative proportion, that means a ratio or a quotient of concentrations. So specifically, KEQ would be equal to, in our case, concentration of N2O4, which is our product, to our concentration of NO2, which was our reactant. And if you notice, this reaction is not a one-to-one, and we need to account for that when we craft an equilibrium constant expression. So to show that because we're reacting two NO2s to create one N2O4, we need to square this concentration term for that particular substance. And this is the proportion of reactant and product. And again, this is an equilibrium constant if these are a proportion of reactant and product concentrations at equilibrium. So sub EQ, these are only true for the concentrations that exist in our state of equilibrium. So we cannot get an equilibrium constant if we are not looking at equilibrium concentrations. So let's look at a general definition. So generally, for reaction A and B, existing in equilibrium with C and D, and let's say that A reacts with little a moles, so that's its balance coefficient, and B with little b moles, so like the mole ratio here is little a to little b, reacts to form little c and little d amounts of C and D respectively. Then KEQ would be a quotient of products, so that is our equilibrium concentration of C times our equilibrium concentration of D, and we need to account for their stoichiometric proportion in this ratio we're building here for our equilibrium constant. So this would be raised to the lowercase c, raised to the lowercase d, all over our reactants. So this would be concentration of A at equilibrium times concentration of B at equilibrium. These again exist in mole ratios that are not just 1-to-1. So I have to account for that in my proportion. So I'm going to raise the equilibrium concentration of A to its coefficient little a, and then raise the equilibrium concentration of B to its coefficient little b. And I have now derived a general equilibrium constant. So this is a relative proportion of equilibrium concentrations in their stoichiometric proportion for anything present in a chemical reaction at equilibrium. So we can get a value that describes the state of equilibrium. Now, the thing about the equilibrium constant that we should keep in mind is that the equilibrium constant, if it is a proportion of concentrations, that means that this can only include things that we can use a concentration to describe. So if we're talking about like an aqueous reaction, we would talk about like the concentration of a solution or a concentration of a solute in solution. But if we were going to look at a reaction that involved pure substances like pure water or a solid, we are going to presume that those concentrations or amounts of those things don't change over time. And also the idea of describing a pure substance in terms of a concentration is kind of like nonsensical, right? Because if I were to hand you like a block of pure silver and ask you to tell me what its concentration was, you'd be like, it's all silver, right? Concentration is part over whole. So we are going to exclude solid and pure liquid phase substances because we're going to make the assumption that during this chemical reaction where we establish an equilibrium, those relative concentrations initially are not going to be very different from those at equilibrium. So we can neglect them from our KEQ expression. So this is the equilibrium constant. In our next videos, we are going to look at how we can specialize the equilibrium constant to talk about different types of reactions. So namely like different phases of reactions. As mentioned, we've been talking about solutions a lot. So we're going to introduce the equilibrium constant for substances that exist in solution. That's called Kc. And then we're also going to revisit our gas phase reactions, like the one that we're seeing here, and introduce the equilibrium constant that we use when looking at an expression of not concentrations of gases, but pressure of gases using what's called Kp. So we'll look at different variations of the equilibrium constant. They are all going to have the same core principle of being a relative proportion of product and reactant concentrations at equilibrium, but we're just now changing them to specialize what kind of reaction we're looking at. So that's coming up.